So welcome to Math341, Lecture 5. If I get out of focus, just do some kind of hand motions and I will hopefully detect. So we've talked a little bit about factorials in the past. So n factorial is the number of ways to order n objects when order matters. It's n minus 1, 3 times 2 times 1. We define 0 factorial to be 1 with the story, the number of ways to order 0 people is 1. There's one way to do nothing. So all Seinfeld episodes are essentially the same. Okay. Gamma of s. We define this to be the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx. This is a really good function to consider. You can view this as x to the s dx over x. And what's nice about this is if I rescale x, if I change variables and send x to 3x, the dx over x is unchanged. So there's a lot of different ways of looking at this. There's some really good calculus exercises you can do. You can show gamma of s plus 1 is s times gamma of s by integrating by parts. So I will leave that as a nice exercise for you to do, that if you integrate by parts, you will get this formula. This is called the functional equation for gamma of s. If you do some brute force calculations, you will get, what do you think the easiest value of s is to do this integral? 1. So you get gamma of 1 is 1, gamma of 2 is also 1. You might begin to think that maybe it's always 1. Then you get gamma of 3 is not 1, turns out to be 2. So you might be thinking maybe it's the Fibonacci numbers. And then you get gamma of 4 is 6. And then you realize, 6 is 3 factorial, 2 is 2 factorial, 1 is 1 factorial, and this one is 0 factorial. And if you look at this, gamma of s plus 1 is s times the previous. It's essentially the shifted factorial. So we get gamma of n plus 1 is n factorial. It's unfortunate that there's a slight shift in definition, but it turns out it's more convenient to define it this way. Why do we care about this? Well, when we have problems in combinatorics, we have factorials all over the place. We want to understand what happens when n is large. What does n factorial look like? So later in the semester, we will talk about Stirling's formula and ways to estimate what n factorial is. The idea is we have this integral representation. So we might be able to use techniques from what class? Calculus is not a bad idea, but not calculus this time.
Differential equations.
Not quite differential equations. I would go real analysis. Or you could also use complex analysis here, but it's advanced analysis. So when in doubt, in this class, the go-to of what we need is real analysis, or occasionally complex analysis. We now have a function which makes sense for all values of s. It agrees with the factorial function when s is a positive integer. And in fact, it extends the notion of factorial. And in fact, because of this functional equation, you can even define things at negative numbers and just extrapolate. So if I want to do gamma of 1/2, according to this, gamma of n plus 1 is n factorial, so this should be 1/2 minus 1, or negative 1/2 factorial. It turns out this equals the square root of pi. This will be extremely important later in the semester. How many of you have done the normal distribution, the bell curve, the Gaussian? This is what's going on with the normalization constant. It's actually gamma of 1/2. This does not mean that if you have negative half of a person, the number of ways you can order that negative half of a body is the square root of pi. Okay? You have lost the combinatorial interpretation once you are no longer an integer. That's fine. But it still turns out to be useful. Okay? Now, there is no wrong answer to this problem. Or at least, there's no wrong answer. But there are answers that are better than others. How might you define n factorial factorial? What's your first thought? Yes.
You start with n factorial, and then do the same process that you did above, bring it out.
And bring it outside. So it's the factorial of n factorial. That is a perfectly fine thing to define. It turns out that's not how we define it because it's not useful. It's not what comes up. What actually comes up in practice is n times n minus 2 times n minus 4 down to either 1 or 2, depending on whether or not it's even or odd. It's not wrong to define n double factorial like this, but it's just not going to be useful because that's not what shows up in problems. Okay? So you always have to think about how do you want to define things. You want to define things that you're going to be using again and again. You want your notation to be good and clear. Here is terrible notation. What did I just write down? There are two acceptable answers for this. Yes? So this one possibility is this is arc sine, which is the inverse to the sine function evaluated at x. And the other one? It's 1 over sine of x. And then not the same. This is why it's actually good notation to use things like arc sine to be clear what you mean. There's a lot of bad notation in mathematics. What's 1 over sine? What do we call that? Cosecant. Is it still in focus this far? All right. So if I had my choice, I would associate probably sine with cosine. I'm sorry, sine with secant and cosine with cosecant. I put the sines and the cos together. We go the opposite way. You can define things however you want. You just need to be aware. But when things are unclear as to what do we mean, then you might put in parentheses and have a little extra notation. Okay? So I like to use things like arc sine. We will be using arc tangent a few times in the semester. All right. So we've done the basics of binomial coefficients. What I want to do now is I want to prove some properties of binomial coefficients with a very powerful method called proof by story. Right. How many of you have seen proof by story? Okay. For a lot of these, there's proof by brute force. Proof by brute force is nice in that it will give you the answer, but it's often inelegant and you often don't have a deeper appreciation of why is it true. I want you to get a sense of why things are true. So we will recall that n choose k is n factorial over k factorial n minus k factorial. It's the number of ways of choosing k objects from n when order doesn't matter. N factorial over n minus k factorial, that's the number of ways to choose k objects when order matters. Divided by k factorial just gives me now the number of unordered ways. So the first result is n choose k is the same as n choose n minus k. Okay? Is it in focus over here? Yes? Excellent. You could prove this by brute force and just multiplying everything out. But let's prove by story. I think I did the Free Willy story last time I taught this, so I'll do Dr. Seuss and the Sneetches. Who knows about the Sneetches on the beaches? Who are the good Sneetches? No! You did not learn from your Dr. Seuss. They're all good Sneetches. I apologize for those of you who have not yet read about the Sneetches, but the moral of the story, shocker, is that all Sneetches are good. But in the beginning, there is a huge debate among the Sneetch community as to who are good. And initially in the Sneetch community, whom are viewed to be good? With the stars upon stars. Right? The ones with stars on their bellies are considered to be the good Sneetches. Okay? So here's two ways of looking at it. Choose exactly k to get stars. This is the positive way of looking at things. I am giving something to k. What's the negative way of looking at it? I'm sorry?
Taking away n.
Yeah. Exclude n minus k from getting stars. So what we're basically saying is, if I choose k people to be in my group, that's the same as choosing n minus k people to exclude or not be in my group. So this is the story proof that the two are the same. Okay? Any questions on this example? You could prove this by straightforward algebra. This is not so bad. But the examples get a little bit more involved as we go deeper and deeper. All right. So for the next one, I want to talk a little bit about the binomial theorem and Pascal's triangle. So we will use the binomial theorem a lot when we start getting to, not surprisingly, binomial random variables. So x plus y to the n is the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k. And we will often take x to be some probability p, and then y will be the probability of 1 minus p. So this will count how many times something happens exactly k times. So imagine you flip a coin with probability p, all the tosses are independent. This will count the probability of having exactly k heads. Okay? So this is an extremely useful result. You might remember Pascal's triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and thank God I'm running out of space, 1, 5, 10, 10, 5, 1. So every number is the sum of the two above it, unless you're on the outside, in which case you're a 1. And if you want, you can just view that there's zeros floating over there. When you expand these numbers, these are the coefficients in the expansion. And we're just putting them into a triangular array. I will show you some interesting patterns about this triangle later in class. If you want to think about this, if I have 5 factors, if I'm looking at this row, if I want to have exactly 3 x's, then that means I choose 2 out of the 5 factors to give me an x, and then the other 3 out of the 5 are going to be not x. So the big relationship that I've mentioned here is that n plus 1 choose k plus 1, so this will be our second fact, is equal to n choose k plus n choose k plus 1. Right. This is the Pascal relation. So I'm going to prove this. One way to prove this is to just write out what all these n choose r's are, clear the denominators, and simplify. It's not elegant. It doesn't give you a sense of why it's true. So let's prove it by story. All right. I actually already did this in my problem-solving class earlier this semester. Let's see if you guys can do a better job. I need a really good, awesome school. These are the snowball marshmallow questions. Nobody can think of a good school. Williams, okay. So we have n people from Williams. I'll assume that the issue was there are just so many good schools in the nation, it's hard to choose just one. But maybe the corresponding question is a lot easier. Is there one school that's just so bad that it's clear if I ask for a bad school? Amherst, that was much faster. So imagine we have n plus 1 people, n of them from Williams and 1 person from Amherst. And we want to form a group of k plus 1 people. So choose k plus 1 from n plus 1. Well, one way to write that is it's just n plus 1 choose k plus 1. And then we're going to count this 2 different ways. And we can focus on whether or not we are stuck with that person from Amherst. If we take them, how many ways is there to choose the person from Amherst? How many ways are there to choose that one person from Amherst? 1. How do I want to write 1? What's the most pedantic way of writing 1? I could write it just as the number 1, but I want to write it far more pedantically. 1 choose 1. If I don't choose the person, how many ways are there not to choose the person? Also one way not to choose them, and how would I write that? 1 choose 0. Now that I have the person from Amherst, I need to get k plus 1 people total. I've got 1 person. How many people do I have to choose from Williams? I'm sorry? not n, k. And how many ways are there to choose k people from the n Williams people? And choose k. And similarly over here, how many Williams people do I need now?
N choose k plus 1.
So I need n choose k plus 1. And so here's a proof. This is proof by story. This is the Pascal relation. Now, in practice, in books, they will just drop this because this is 1, and they'll drop this because this is 1. For the most part, we'll drop it when we do calculations, but it's nice to put it there because it really highlights what's going on, and it gives you an idea of how to try to avoid making mistakes in problems like this. I've got n plus 1 people in play, and I've got to choose k plus 1 of those n plus 1 people. Notice the top sums to n plus 1 in both cases, and the bottom sums to k plus 1 in both places. This is a good way to see that I haven't made a mistake. That in each place, I'm adding up to n plus 1 people upstairs, and I'm just dividing them in different ways, choosing in different ways. Yes?
How are you adding the top part? You just multiply.
No, well, I'm saying the sum of the two pieces in the top, the n and the 1, add up to n plus 1. The sum of the two things in the bottom. In terms of what this value is, I do not add the tops and do not add the bottoms. But I'm just saying, I have n plus 1 people in play, and notice that the sum of the tops is always adding up to n plus 1. I have to choose k plus 1 people. Notice the bottoms are always adding up to k plus 1 people. All right. Any questions on this? Yes? This is an actual proof. It is probably not called proof by story. This is my notation for it. But you're telling a story and you're computing something two different ways. So I've calculated how many ways there are to choose k plus 1 people from n plus 1 people two different ways. One way it's this, one way it's this. Since I'm describing the same counting problem, they must be the same. So the challenge in a lot of these proofs is to come up with the story. So I was debating whether or not I should do one more. Let's do one more where the story is not as clear and you have to do a little bit more work. So let me move back a little bit. Reasonably close? All right. So the sum, k goes from 0 to n, of n choose k squared is 2n choose n. Okay? The story is not quite as clear here as to what's going on. The first thing to note is the sum k goes from 0 to n of n choose k squared is the same as the sum k goes from 0 to n of n choose k, n choose n minus k. Okay? Imagine we have n smart students from, I could just say n Williams students, and we have n people from some school that need a little extra tutoring. And we're going to look at ways to pair things. And now I'm going to form a group of n people. So I want n people. How many ways are there to choose n people from n Williams students and n Amherst students? Two n choose n. And that's exactly what this is here. So the answer is 2n choose n. If I have a group of n people, there must be some number from Williams. Let's call that k. If we have k people from Williams, how many people do we have from not Williams, also known as Amherst? N minus k. So this would be number of Williams times the number of not Williams. And then we just go over all possibilities. There could be no one from Williams, one person from Williams, all the way up to n people from Williams. And so when the dust settles, you get that it's 2n choose n. This is a much harder story proof. One of the things that's hard is you have to realize you have n choose k squared. You want to write that as n choose k, n times n minus k. If I gave you n choose k cubed, that's probably not going to have a nice story. So as a nice exercise, what might be a nice product of 3 binomial coefficients that would have a nice story? So can you come up with the object? This is almost reverse engineering. What can I solve? And then I'll create a problem around it. All right. So there are a whole slew of identities we can prove about binomial coefficients. Later on, I will talk a little bit about how you might try to calculate these efficiently. Any questions on binomials before we move to poker? We will not be playing poker for money. We will be treating poker as a theoretical exercise. And because this is being recorded, I am not advocating any of you apply this knowledge to win money at poker. If you do, however, I do want you to remember where you learned this knowledge. But for legal reasons, I am not encouraging you to play poker for money. So what I want to do is I want to talk about calculating poker hands. So just to make sure we're all on the same page, most decks have 52 cards. You might have 2 jokers. We won't play with the jokers. So 52 cards. You have 4 suits: spades, hearts, diamonds, and clubs. And for those of you who love to do LaTeX, there are LaTeX commands, of course, for all of these suits. Each goes from ace, deuce, 3 to 10, and jack, queen, king. Sometimes ace is allowed to be both high or low, but there's 13 cards. And you want to calculate various hands. Sometimes you might have cards are wild, like maybe deuces are wild, or one-eyed jacks and suicide kings are wild, and then that changes the probabilities of different hands. And so one of the things you want to calculate is what's the probability of getting a hand. Frequently hands are 5 cards. So how many 5-card hands are there? 52 choose 5. So we will assume that the order does not matter. In a lot of card games, the order does matter because you bid after, or you bet after, certain cards are turned over or dealt. And then, it matters if you are dealt ace, 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 7, 9, or 7, 9, ace, ace, ace. You get those aces very quickly. You will bid a lot differently than if you get 7s and 9s. If not, we need to really talk about bidding. Okay? So now let's look at various hands. So a full house is 2 of a kind and 3 of a kind. Two pair is 2 of a kind and 2 of a kind. So if I give you jack, jack, 4, 4, 4, what is this? Is it also 2 pairs? This is not an English class. So we will just declare in a class like this that we will not view this as 2 pair. We will view this as this has a full house. But you want to be very careful when you talk about things. Here I'm saying I have exactly 2 of one and exactly 3 of another. If I say I want to have 2 jacks and 2 4s, does this count as 2 jacks and 2 4s? Yes. So for the question of 2 jacks and 2 4s, this would count. It would also be a full house. It would count a little bit differently. So what I want to do is I want to calculate what is the probability we have a full house. All right? So probability of a full house. And the way you do all these calculations is you count how many ways are there to get a full house, and then you divide by the number of ways to get a 5-card hand, and then that will be the answer. Imagine that you are not good at combinatorics, and you can't do the calculation at all, but you really want to know what the probability is, or at least a close approximation. What could you do? Test it. Right. I was wondering if somebody was going to say go to Google, go to Wikipedia, look up, poker hands. I was going to have an electromagnetic pulse detonate over the United States and destroy all of our circuits, but good. Run a computer code. And I will talk in a few minutes about how you would write a good computer code to calculate this. For a lot of problems, a bad code is sufficient, but I want to get you some good habits. So let's try to calculate the number of ways. There's a lot of ways to do this. So one way to do this is I have to choose two numbers. So one number I'm going to have 3 times, one number I'm going to have twice. How many ways are there to choose two numbers? 13 choose 2. And then how many ways are there to choose which one of them is the one that occurs 3 times and which one occurs twice? 2 choose 1. Another way of doing it is I have 13 ways to choose the first suit, and then later I'll have 12 ways to choose the second suit. And what's going to really happen is this 2 choose 1 is going to cancel the 2 factorial there. There's lots of ways of doing this. All right, I've chosen my 2 numbers. Maybe I chose jacks and 4s, and the jacks are going to occur twice, and the 4s are going to occur 3 times. How many ways are there to choose 2 of the jacks? 4 choose 2. And now, how many ways are there to choose 3 of the 4s? 4 choose 3. So these 2 will be the same. And then all you have to do is divide by 52 choose 5. And that will give you the probability. Okay. Any questions about this calculation? Yes?
Where did you get the 2 choose 1 top? What is that?
So I choose 2 numbers. So
Oh, okay.
choose 2 numbers. And now choose which happens 3 times, which happens 2 times. So again, there's lots of different ways you can tell the story. In fact, if you can tell the story more than one way, should you? Yes. If your answers match, does that mean you're correct? No, but you get a little bit more confident. If your answers don't match, what do you know? I'm sorry? At least one of them is wrong. It's possible both of them are wrong. If you have 2 numbers that are wrong, then if possible, you should write some computer code. So I want to talk a little bit about computer code. I probably shouldn't have raised the very top, but all. So I want at least 2 kings, at least 2 queens. And we have 5 cards. So we could go through and we could do the calculation. And I could have something in the form king, king, queen, 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 king, 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 queen, queen. Or I could have king, king, queen, queen, and n, where n is not a king and it's not a queen. We have to be very careful. This is one of the most common mistakes people make in probability. Is they said, well, I want to have at least 2 kings, so I would choose 4 choose 2, I choose 2 kings. I want to have at least 2 queens, so I choose 4 choose 2 cards there. And now I need 1 more card. How many cards are remaining? 50.
48.
I'm sorry?
48.
48 cards are remaining, because we've chosen twice here and twice here. The bottom adds up to 5, which is good, but what does the top add up to? It adds up to 56. The top is adding up to more than 52. This is an indication that we may have made a mistake. It looks like I have more cards in play than should be. And what goes wrong is, imagine I have the king of spades, the king of clubs, and now this card is also a king. So this is being counted as a king of spades, king of clubs, but if this is the king of hearts, it would have also counted as a king of spades, king of hearts. And it would have also counted as a king of hearts, king of clubs. I'd be counting something too many times. So when I do it like this, it's very important. I've chosen exactly 2 kings 4. I can't choose any more kings at this point. The kings are no longer available. So you would have to break it up into calculating all of these. This isn't bad. This would be 4 choose 2, 4 choose 3. This would be 4 choose 3, 4 choose 2. And what would this one be? Instead of 48, what should it be? It should be 44. And now you would see. And if you wanted over here, I said that this was 4 choose 2, 4 choose 3. What's the last one really, if you want to be super pedantic and waste chalk? What should I really put here? Not 48. 44 choose 0. To be exceptionally pedantic, I choose 2 of the 4 kings, I choose 3 of the 4 queens, and I choose no remaining cards. And now the tops will add up to 52. So again, whenever you can formalize things and have a recipe that minimizes your chance of making a mistake, it's good to do that in the beginning. When you get really comfortable and confident, you don't want to keep writing in factors of 1. All right. So let's talk about how would we program this. Because a big part of this class is I want you to be able to write code to estimate this. So what would you need for your code? What's the first thing we would need? Yes? Deck of cards. So how do you want to create the deck? What should the deck be? 1 to 52. Okay. We're going to start with this, and then we'll try to make the code better.
Use 0 to 51. You're programming.
Depends on the environment. Sometimes it's better to do. It really depends on how you want to look at things as to which is better. This is nice because it ends with a multiple of 4 or multiple of 13. But it would work either way. How do you tell how many kings you have and how many queens you have? This is starting to get really involved, right? Did I talk to you about Galileo's experiment where he dropped the 2 spheres? Did I mention that in this class? Right. And what was the question I asked you? What color? And this is who gives us, right? It has nothing to do with the problem. You want to focus on the essentials. What I could do is maybe 52, 51, 15, 49 are kings, 48, 47, 46, 45 are queens, and then make sure I have at least 2 of each set. That's more involved. I only care about kings and queens for this. I'm not trying to write the most general code, right? I'm only trying to write a code that is sufficient for this problem. So what I will do, and then let me toggle this, so hopefully this will be in focus. Okay. Is that so good? Yeah, this is the problem. So if it's not good, I'll be sending the file. So now I'm going to have my deck defined as follows. If the number goes from 1 to 4, I'm going to put in a 1. If I go from 5 to 8, I'm going to put in a 10. And if I go from 9 to 52, I'm going to put in a 0. This is a really efficient way to code this. Because if it's not a king or queen, I don't really care what it is. Let me just make those zeros. And now when I take my hand, how do I tell how many kings I have? Well, kings are valued at 1. Queens are valued at 10. If you just sum up the numbers in your hand, the 1's digit is going to be number of kings. And the 10's digit is going to be number of queens. This is a really fast, efficient way of doing things. You could do it the other way. The other way would work. It's just more coding. If you could spend some time before you do your programming and think, what am I really studying? What do I really care about? There's often tremendous savings. And now all I have to do, this over here is just printing out every 10% to just let me know how long it's gone. Because if I don't have some idea of how much the program has run, I might be very close to it finishing, but getting so frustrated I just abort. So I want an update. So Mathematica has a lot of really nice commands. One is random sample. It randomly chooses, in this case, 5 cards from your list called deck. And now I just sum the values. If the value is greater than 20, I know I have to have at least 3 queens. I have to have at least 2 queens. So if my value is at least 20, I know I have at least 2 queens. Now I look at the ones digit, so take the mod of the value mod 10. So it is, we'll call it 11 o'clock right now. I'll round up. What time will it be in 4 hours? Everybody agrees that it's going to be 3 o'clock in 4 hours from now if it's 11? So you've all just told me that 11 plus 4 equals 3. How many of you have not taken abstract algebra? I technically have never taken abstract algebra, so my hand has to be up as well. I've taught it, I just haven't taken it. So for those of you who haven't taken abstract algebra, you will spend a lot of time on stuff like that if you make it to that class. And this is called modular arithmetic, or not surprisingly, clock arithmetic. And we say 2 numbers are equivalent if they differ on a clock by a multiple of 12. You don't have to use 12 hours. You could use metric time. You could have 10 hours. And so here, I'm just looking at the ones digit. This gives me a nice way of getting the ones digit. And now I want the ones digit to be at least 2. And if that happens, then the success is increased by 1. So I found another one that worked. And then what I'm going to do is my success rate is 100.0 number of successes divided by the number I need to do. So this is my code. I'll compile the code. And now, let's run it 10 times. And it found none. So the probability of getting at least 2 kings and at least 2 queens is essentially 0. Do you agree with this? Why not? Yeah, this is not large enough. What are the only percentages I can observe? 10%, 20%, 30%. If I flip a coin once, what are the only possible outcomes I can get for my guess for the probability of heads? 100% or 0%. So I might think it's probably below 10%, but I really don't have much data. All right, let's bump it up. Let's do it 1,000 times. It still runs extremely fast. And now we get a very small percentage. We could do it, a little bit more, putting a few zeros. So this would be 10 million times. And now you can begin to see it's taking a while. And this is where my impatience starts to get in. And I haven't even done, okay, so now I've done 10%. So now I have some estimate as to how long it will take. If you look closely, you'll see that I have surrounded it in something called timing. So timing tells you how long it takes to do. So if I make this 1,000, the timing was 0.015. So if I do 10,000, let's do 100,000. That's enough to be a little bit more accurate. So the success rate is very small. It's taking about 0.82 seconds. So if I were to do this 10 times longer, if it took 0.82 seconds, about how long would you expect? About 8 seconds, 8.2 seconds. And the reason is this is a problem that scales very nicely. It's not going to get harder as you go further. I'm just doing the same simple calculation, and 7.8, that's within reason. If I were to go up now from 1 million to 10 million, now we're talking about on the order of over a minute. I really do not want to waste an entire minute of class time doing this. All right? But it's good to get a sense. You can then compare what the observed success rate is to what the actual answer is. Once you get up to 10 million, it's not bad. If you did 100 million, it would be very good, and you can easily get that done within an hour or two. So if you had a homework problem, you could just have the code running. All right. Any questions on these calculations? Yes?
Are we limited to what program we could use?
You can use any program you want, any environment you want. I don't care, whatever you're comfortable with. I just care that you have the skill. This is very similar to if you write a math paper with me, I really don't care how you do the bibliography. To me, the purpose of a bibliography is to find references. I don't care about the Oxford style or the Chicago style or any of these things like that. I know it makes some people very happy when the references are formatted in a certain way. No. Whatever language you want to use is fine to do the simulations. Different languages have different commands that are nice. Mathematic has a nice random sample command, which is nice for this. R, I'm sure, has something similar. All right. What I want to do is I want to end with Pascal's triangle. And so what I'm going to do is I'm going to look at Pascal's triangle, and if my number is odd, I'm going to put a blue dot, And if the number's even, I'm going to just leave it empty. And so Pascal's triangle goes infinitely far down. I don't have time to go infinitely far down, so I'll do a finite approximation. Also, instead of having the triangle come down, I'm actually going to have the triangle going right to left, or left to right. Really not a big deal, just rotate your head. Now the other thing is you take more and more rows, I'm going to have more and more screen. So what I'm going to do is I'm always going to adjust the display so that it always displays it in essentially a unit square. So it's just going to rescale so it always fits in the screen. Okay? I wrote this code in Mathematica. I could not find something on YouTube online that actually had this. I was shocked. What I've arranged to do is Mathematica has a ability to manipulate. So I'm going to just do different screenshots with different number of points, and I can control the speed. Right? So it will start off slow, and it will get slower just because Mathematica is having problems displaying everything. And then hopefully you will notice a pattern emerging. Okay. Pattern might not be too clear at this point. So is the pattern becoming clear? So again, you're just getting more and more rows. I'll speed it up a little bit. Hopefully at this point the pattern is beginning to become very clear. Anybody know what word I should say? Fractal. So there's a fractal structure. Instead of looking at things as to whether or not they're even or odd, you could do what their remainder is when you divide by 3 or 4 or 5, and you can play other games and get multicolored pictures. So this part here gets repeated here and here, then this whole part gets repeated here and here, and then this whole part gets repeated here, and then so it just keeps going on and on and on like that. So if you wanted to code this, there's a lot of different ways you could code this. The reason I want to talk about this is I want to really emphasize solving the problem you need to solve and not the problem you think you need to solve. So again, if you love computer science and you love recursion, there's a lot of great ways to do this with recursion. Other things we could do is we could try to figure out, well, how do we compute the next row given the fact that maybe we know the previous row? Maybe we keep the previous row in memory and use that to get the next. Oh, well, if we do that, is it easy to get one row if we know the previous row? Yes. But the previous row actually might be a lot of memory to store as this gets very, very large. So the question becomes, what's the most efficient way to compute this? I am not going to tell you what the most efficient way is. I just want to discuss some of these issues. And the reason this matters is when you do your simulations, you want the computer to be able to run long enough to have a good confidence in the answer you get. And that's why sometimes these slight improvements in code will become very important. Right. So let me end just a little bit with some thoughts on coding. So we could use previous row. But this is memory intense. I am sure a really good CS student could write a program in one line to calculate this beautifully with recursion and display it. Here's another approach. N choose k plus 1. This is n choose k. This is n factorial over k plus 1 factorial n minus k plus 1 factorial. This is n factorial over k plus 1 times k factorial n minus k minus 1 factorial. Remember, we're marching down the row. We know what n choose k is. We know if that's a 0 or 1. This looks a lot like n choose k. What is this screaming to add? What does this want? What factor does this want added? What factor does this want incorporated to it? What factor?
K. Or n minus k.
N minus k. Can I just multiply the denominator by n minus k? No. If I multiply the denominator by n minus k, what do I have to do upstairs? I have to put in n minus k over here. And now we get n minus k over k plus 1 and choose k. So if you know a binomial coefficient, then the next one is just n minus k over k plus 1 times that. Now, unfortunately, if we just store if this is a 0 or 1, then we're in trouble, because this is not always going to be an integer. So you might have to keep the values, but you can use this to just march down, and it keeps the multiplication from getting too bad at any point. So there's lots of different tricks like this. All right, I'll end up with just one last programming trick. How many of you have ever done a Sudoku? So if I want to make sure a proposed Sudoku is correct, how many row checks? I'm sorry?
And then on the board.
So let's say it's let's say it's in a 9 by 9 Sudoku. So how many row checks do I need? I'm sorry? I can't hear you. 9. And for each, what does it mean to check a row? I've got to check and make sure I have exactly 1, 1, exactly 1, 2. So maybe it's 9 rows, maybe 9 checks per row. And then you would have the column checks, and then you would have the big block checks. So that's a lot of checks to do. It's not horrible for a computer. It'll run through it very quickly. But what I want to show you is very similar to the king-queen problem. If we change our notation, it's a little bit easier. Does it matter that we use the numbers 1 through 9 for Sudoku? Could I use vegetables of the world? Yes, I'd probably have trouble drawing them. Let's use instead 1, 10, 100, 1,000, ... all the way up to 10 to the 8. And now just calculate the row sum and compare to 111,000,000, 111,000, 111. The only way, if I use the numbers 100, 110, 100,000, and so on, that I can get 111,000,000, 111,000, 111 is if I have each number once and only once. So I just have to do that simple sum. If I use the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, I could have every number once, and I would get, I think, 45. Or I could have 2 2s and 2 8s. Question?
So are you saying that it's the number of calculations that matters more than the size?
I'm sorry?
It's the number of calculations that matters more than the size?
No, what I'm just saying is just in terms of like a coding perspective. Rather than coding 9 checks for each row, do I have a 1? Do I have a 2? Do I have a 3?
You mean it's easier to code?
It's easier to code. All I have to do now is check and see, does the row sum to 111,000,000, 111,000, 111? The only way it can sum is if I have one and only one of each number.
How do you approach the problem for a square, like the subsquares?
I'm sorry?
Like for the subsquares in the Sudoku, how do you approach that problem?
What's the sum square?
Like the subsquare. Like
Oh, the subsquares. You would just add up all the elements in the subsquare. And you see, does that add up to 111,000,000, 111,000, 111? And you would just have 9 of those. So it's the same idea. Again, what I want you to get out of this is the mix between theory and practice. It's not enough to just know what the answer is. You want to be able to work with it. We will shift gears, and on Wednesday, we will actually talk about probability and modeling. This is one of the main reasons you take a class like this, so you can design models and see how well it describes things. All right.